This video will cover what oscilloscopes do. A follow-up video will look at the specifics of making some measurements with them. This oscilloscope happens to be the model that you'll most likely be using in lab, but all oscilloscopes are pretty similar. What mostly changes is how the screen and controls are laid out, so make sure you learn what everything does rather than where it is. That way you'll be able to use any oscilloscope you come across. Oscilloscopes measure voltage. The inputs are along the bottom here. There are almost always at least two channels like on this scope, but some scopes have more, and they're usually called channel 1, channel 2, etc. The inputs use a type of connector called BNC, which allows you to easily connect probes by slipping the connector on and twisting it to lock it in place. The most common type of scope probe looks like this. This type of probe uses an alligator clip on the side as the ground reference. You should always have it attached to a local ground in your circuit for measurements you make in 2031. On the tip of the probe is this retractable hook that can clip onto wires. This is where the oscilloscope measures the voltage. If you need to probe a small spot in your circuit, the tip of the probe can be removed to reveal a sharp probe tip. Oscilloscopes display the measured voltage vertically on the screen. There's always a marker on the screen that indicates the 0 volts position for each channel because that 0 position can be moved up and down so that you can place the signal where you want on the screen. The screen will also display the current vertical scale. On these scopes, it's displayed down here in the channel information. You can adjust the scale to fit higher or lower voltage signals on the screen. Here's an example. With nothing connected to the probe, the signal trace is at 0 volts as expected. If I connect this 9-volt battery, the trace moves up. We can find the voltage by taking the current vertical scale, 5 volts per division, and multiplying by the number of divisions. From 0, this trace is just over 1 4/5 divisions up, which means that the signal has a voltage of just over 9 volts. If I change the vertical scale and move the 0 point, the voltage itself doesn't change, it's just displayed differently on the screen. Now it's 2 volts per division times 4 3/5 divisions, which is about 9.2 volts. If you just want to measure voltage though, you would use a voltmeter. The reason to use an oscilloscope is that they can record and display how a voltage changes over time. Here's an example. If I connect the battery from before for 1 second, the oscilloscope shows how the voltage changed over time. Like the vertical scale, the screen also displays the current horizontal scale. At this current scale of 500 milliseconds per division, this pulse spanning about 2 divisions shows that I had the battery connected for about 1 second. A time scale on the order of seconds isn't very interesting though. The reason oscilloscopes cost thousands of dollars is because they can measure voltage really quickly. This model can sample it up to 4 billion times per second, and that's not even very impressive as far as oscilloscopes go. Sampling that quickly allows you to view very fast or very brief signal changes. For example, in Lab 2, the lab manual mentions switch bounce, where the contacts of a switch will connect and disconnect several times as they bounce off of each other when coming together. Using an oscilloscope, you can capture that event actually happening and measure things like how long the bounce lasts. This switch bounced for about 1.5 milliseconds. You might be wondering, if an event happens in only a few milliseconds or even microseconds or nanoseconds, how can you see it on the screen? Well, when running at higher speeds, the scope doesn't display all of the data it acquires. Instead, it records a screen's worth of data and displays it all at once, leaving it on the screen long enough for you to see it. But still, if you're trying to capture a certain event, how can you make sure that the scope captures the right instant? The answer is triggers. Oscilloscopes have a feature that monitors the measured signal watching for a certain event. Here I've configured the scope to trigger on falling edges of the signal. What this means is that if the incoming signal crosses this threshold, called the trigger voltage or trigger level, from high to low, the scope will record data before and after that event and display it on the screen with the event itself located horizontally at a specified point, usually marked with an arrow at the top or bottom of the screen. Note that the trigger level is also displayed on the screen with an arrow on the right side. Every time I press the button, the scope captures the falling edge of the signal and displays it on the screen. Triggers allow you to capture brief events, but they have another very important benefit. You'll very often be using a scope to look at a repetitive waveform like a square wave. Without triggers, the oscilloscope would be displaying random pieces of the waveform, and it would be very difficult to see the waveform clearly enough to make measurements on it. But with the trigger set up correctly, the oscilloscope will always display the waveform at the same place on the screen. Even though the scope is continuously capturing new data, the waveform appears static because it's periodic and each new acquisition is overlaid perfectly with the previous ones. To sum up, the main points are that oscilloscopes plot voltage on the vertical axis over time on the horizontal axis and can be configured to capture specific events by setting appropriate trigger conditions. Oscilloscopes are one of the most powerful diagnostic and validation tools available to electrical engineers, and with this basic information about how they work, you're on your way to using them effectively. See you next time.